So one thing that we've been talking about in some of the papers that we've looked at, especially with organic compounds, is this thing called the octanol water partitioning coefficient, or KOW. That's what's this KOW here. So what we do is we use octanol as an example of an organic molecule. So what we do is we just assume that it's like a generic organic molecule. So it's organic in the system, in the soil, and stuff like that. And so we represent this as a generic organic compound. And we compare how our chemical that we're concerned with compares to octanol. So we have octanol sitting with water, and we look at it, how much does it diffuse into the water? So how much solubility does the octanol have with water? And then we compare that to the concentration in the water. So the concentration of we have the octanol water partitioning coefficient as our KOW. And this is the relative tendency of the organic solute to partition into an organic material. So we have our KO over KW, where KO is the concentration in octanol, and our KW is the concentration in the water. So we have octanol and water in here. We mix these two together. We have these separated here. We mix in our chemical into there, and we find out how much of it goes into the octanol, how much of it dissolves inside of the water, and we do a ratio of those two, and then we end up with the KOW for the system. KOWs range somewhere between 10 to the minus 3 to 10 to the 7. So if they're greater than 10, then they're hydrophilic. If they're less than 10, they're hydrophilic. If they're greater than 10, they're hydrophobic. And so we usually don't say 10 to the third KOW. What we usually look at is what's called the log of the KOW. And so basically we're just looking at these log units. And that's what you normally will see. When I've done these type of experiments and looked at these things, we usually just give like, oh, the KOW is 7. But that actually, there's maybe some numbers that come up, and 2.3 times 10 to the 7. We ignore that, and we just look at the exponentials. Like a lot of things, even the hydraulic conductivity, we just look at the exponentials. We concern ourselves with that, so we usually just look at the log of KOW inside of a system, and that's the number that we use for this octanol water partitioning coefficient inside of there. And so this is how we determine. So I just wanted to give you guys some examples here. So like we know some of these compounds here. So we've talked about benzene before. Its solubility in moles per meter cubed. These are relatively hydrophobic compounds. So benzene has a solubility of 22.8 moles into a meter cubed of water. So the KOW is 100, and the log KOW is 2. So this is what we're talking about down in here when we talk about 2 and 1, stuff like that. I'm sorry, that's the referring to this number here. TCE is 7.6, so it is less soluble inside of the water. So it has double the KOW, so it's a log of 2.3. So it's so that comes into here. So we have PCE is 2.4, so 400. So 2.6, and then lindane, which is 2.10 to the 10 to the minus 2, 8,000. And so what this is more mobile, and this is less mobile inside of the system. So lindane, as having a log KOW, there's more absorption in here. There's less absorption for the benzene inside of there, so it'll move faster than a number that's in that system. Now, if we get into hydrophobic compounds here, let me move me over here. We can get into hydrophobic compounds, and we can get into anthracene, which really has no solubility in water. And so its KOW is 3 times 10 to the 4, so it's 455, so it's strongly attracted to organic molecules. We can get into DDT, which is good for you and me. That is 10 to the 4, so this comes 10 to the, I think it's 8, and then or 10 to the 6, so we get a 6 here. And then dioxins, we can get 10 to the minus 7, and so we have a 6 here, so we have 6.7. So these are strongly attached onto the organic compounds in here. And then we can get things like PCBs, which have even organic compounds inside of there too. So we can use these octanol water partitioning coefficients in order to determine how the systems, how much absorption will occur for organic compounds. We can look these up. So as in this table here, you can look up KOWs. These are standard things to know for most organic compounds. So with hydrophobic partitioning of compounds, let's look at the KDs. And many of these nonpolar or weakly organic molecule compounds are absorbed mainly to the soil organics, with only a small proportion sorbing onto the minerals. So this is where you really need to know what the organic compound. I don't know why it's doing that. Let me put my hand there, and maybe it'll stop that flashing. And so what we actually have to do with these particular compounds is look at the amount of organic carbon that's in the system. So what we try to do is, because these things are dependent on the thing, our KD in the system equals our KOC times our FOC, where KOC equals the distribution coefficient for solutes with organic for the solute with organic carbon in the soil. So this is for a solute with organic carbon in the soil. And then our FOC equals the mass fraction of organic carbon in the soil. So we have to know how much organic compounds, how much organic carbon, so that's what the OC stands for, organic carbon. So the fraction of the organic carbon times the KOC will tell us there inside of our systems. Now, this is just for the organics. Now, we assume everything is in there. Now, we could add on to the amount that is absorbed onto the mineral fraction and other parts of it. We assume those things don't matter for organics, because, again, this is for organics. We don't assume that there's much onto the mineral fraction, so we just assume this all goes to 0. So we ignore the amount that is absorbed onto the mineral for organics. All we're looking for is the amount of organics. So if we know what the fraction of organic carbon is, and we know the distribution onto our system for our KOC, then then it'll tell us into there. So for organic rich soils like we have around here, where the FOC is greater than 0.01, absorption of the most hydrophobic compounds like benzene, TCE, DDT, PCB will be completely dominated by this KOC and the FOC here. However, when we have very low organic compounds, then minerals might become more there and stuff like that, but we generally are not concerned about that. It's really much more of looking at the FOC. So how do we figure out this, and how can we actually use this practically and stuff like that? So experimental investigations have shown empirical relationships. So what they found out is FOC, or the fraction of organic carbon, equals the SA divided by 200 KOW to the 0.84, where SA is the specific surface area, of the soil, So something like a quartz sand will have less than 1 meter squared per gram. Let's say a kaolinite will have around 12 meters squared per gram. A smectite. So all of our different clays will have 800, because as you get into them, you get into there. This is our KOW, which we can look up. And so if we know the specific surface area of our soil, we know the KOW, we can estimate the FOC based upon that. So, like say we use an example, we'll use the Borden sand. We've talked about Borden before. So in that example here, the Borden sand has an surface area of 0.8 meters squared per gram. Say we use TCE in that system. We know the KOW for that is 195. And so the FOC star is 5 times 10 to the negative 5. And so this becomes the critical level of soil, of organic carbon, to make this the multiple that it's going to absorb onto the system. So if you have less than this amount of FOC, then we know that we can ignore we can ignore organic absorption into our system. But this becomes really typical. So typically for FOCs for geologic materials are somewhere in these -5, -3 systems like that and stuff like that into there. And so these become very important when we're looking at the system. Okay, so we now have two empirical indicators. We have our KOW, which measures the relative tendency to absorb onto the organic compound, and we have our FOC star, which estimates that range. So it tells us when KD is going to be critical in there. So another man named Kirchhoff and others later on updated this, but usually we refer to this as Kirchhoff, developed a correlation between KOC and KOW, or solubility range of different soils and solutes. So he did and developed equations to predict KOC. So what he looked at was the log of KOC equals 0.63 the log of the KOW. So this was Kirchhoff's in 1979 into that system there. And so if we take it and we look at the log of the KOC equals 0.44 minus 0.54, the log of S, and S is the solubility of the organic compound. So if we know the solubility of the compound, we can come up with a way of predicting our KOC for our system. And so methods provide a useful first approximation of our KOC, which with a value of FOC, so we can find out our FOC, can use to calculate our KD value, which is really important, and then our retardation factor for a given organic compound. So there are limitations to this. So we can get our retardation coefficient because we need to get that retardation factor, remember, we need 1 plus the bulk density over the saturated system, our porosity, times KD. Well, in order to get KD, we needed the solubility, we need the FOC, and then we can get this, and then we can go through all of these things in order to be able to get that retardation factor based upon not just on our an experimental method, but based upon the amount of organic compound, the solubility of it, of the system, and then we can get that KD value. Then that gives us our retardation factor, which then can go into our equations. So this is how we use our KOW and our KOC in order to be able to do some things with retardation. I don't have my new Fetter book here, but this is from the old Fetter book, from the 1993 version of it. So if we want to figure out KOC, and you can look this up in your book and get all these down in here, people have come up with estimations of how to estimate KOC to KOW inside of the systems inside of here. And so they used a whole bunch of different chemicals, and they've come up with different equations inside of there. And so a lot of times this was, for a while there, like people were coming up with different ways of doing these equations and stuff like that, and being able to link these chemicals together. And so it's very important that we get this regression of here of the KOC, log of KOC and log of KOW. They'll vary for the different types of contaminants, and you can look up these equations inside of your book. So if you look this up inside of the book and you look up all these different equations and look at all of this, there is a lot of disagreement, and well, a lot of disagreement, but a lot of like variations, and like they look at the different soil types and the different organics in there, and usually the measured absorption is much greater than the calculated. So that is one of the things you can do there. Well, why is that? Well, absorption to mineral surfaces is still part of it, even though we're kind of assuming it's not in there. sometimes it's hard to measure the FOC into the system. Is the organic compound, the pH, so it's really hard for us to actually model the entire system. But this gives us a great first approximation of how much a retardation factor there is without us actually doing a trial test or looking at the column experiments or doing other things. This is just a way in order to estimate that in order to go into our modeling, especially if we have a new emerging contaminant. Or like we were talking about PFAS, there's 600 different chemicals. So we can look at the retardation of each one of those and then make some predictions as to which one will move further and into our system. The other issue with organics is, I'll move myself over here, is this idea that all of these systems to assume that all the fraction of organic carbon in soil is exactly the same. So it's the same type of carbon, it's the same type of system. But in actuality, when we look at it, we know that there's like old carbon, like we get different types of carbon and they vary in their soil systems. So like the immunohumic versus fluvic acids, what type of carbons are left. So when we leach out all the easy carbons, we get these larger organic compounds, and then that can vary the amount of absorption that goes on into these things. And so we, as researchers, will look into these systems and stuff like that. But again,